So with solubility equilibria, the question is how much of an insoluble solid goes into solution? All right, and this is going to be reflected in its equilibrium constant. So we've had Kas, Kbs, Kcs, Kws, now we have KSPs. KSP is a solubility product. It's the equilibrium constant associated with dissolving an insoluble ionic compound. It's temperature dependent, right? So as we know, different ionic compounds are either more or less soluble at different temperatures. So the KSP value changes like with all equilibrium constants with temperature. So when we talk about the solubility constant for silver chloride solid, we're talking at a temperature like 25 degrees Celsius or something. So I'm not sure, what 1.6 times 10 to the minus 10 is representing. Is it representing 25 degrees Celsius? I'm imagining so. So not very soluble, right? Not very much silver ion and chloride ion is going to be going into solution with a KSP value, equal to 10 to the negative 10. Silver carbonate, even worse, right? Or it appears worse anyway. 1.8 times 10 to the minus 12. Again, notice we only put things that are in solution or gases into equilibrium expressions, so the solids are not included. So these are frankly easier to solve for, right? There's no denominator here, so they're easier values to solve for in terms of how much of the solid goes into solution. When I look at calcium phosphate, it's going to be the calcium ion concentration of the third power times the phosphate concentration raised to the second power is equal to 1.2 times 10 to the minus 26. Again, insoluble, right? Very little of these ions going into solution. All right, like we said, right, the amount of excess solid present has no effect on the position of equilibrium, right? It's a surface area issue. I have an equilibrium established between the return of the sodium ions and the chloride ions in a equilibrium with sodium chloride solid versus escape. So if I double the surface area, I double the opportunity for returning to the solid phase, and double the opportunity for escaping into the aqueous phase. All right, molar solubility, right, as opposed to solubility product, is how much of the solid goes into solution. Right? If we're talking molar solubility, we're talking moles per liter. How many moles per liter of the solid go into solution? And we use the solubility product to solve for that. So get this clear. Right? It was never clear to me, so I want to be clear to you. Solubility product's the equilibrium constant. Solubility is how much of the solid goes into solution. All right, so whereas solubility product is a constant at a certain temperature, the solubility has an infinite number of possibilities because of due to common ion situations. Right? If I put a common ion in there, I affect the solubility of the solid. All right, so given KSP, you should be able to calculate the solubility. How much of the stuff's going to solution? Calculate the concentration of the anion, cation. Well, that goes along with molar solubility. And be able to solve for the molar solubility when you have a common ion. So these are the kinds of problems. The solubility of lead chromate is 4.5 times 10 to the minus 5 grams per liter. What is its solubility product? All right, so we did these problems in the last chapter, right? If you know what the equilibrium concentrations are of the reactants and the products, you plug them in the law of mass action, solve. So it's the same thing here, right? So we plug into the KSP expression, right? The concentration of the lead ion and concentration of the chromate ion in terms of moles per liter. So we use the molar mass of lead chromate to get to moles per liter. And that represents the concentration of the lead ion and the chromate ion. We then take these concentrations, plug them in the law of mass action, and solve for K. Okay, so this is at a certain temperature. The KSP value for lead chromate is 1.9 times 10 to the minus 14. All right, the other kind of problem is calculating the molar solubility, all right, how much of the solid is going into solution when we're given the KSP value. So like the problems in the last chapter, for every X amount of lead carbonate lost, I'm making X amount of lead ion and X amount of carbonate ion. So these are the equilibrium concentrations. We plug X in for the lead ion, X in for the carbonate ion. X times X is X squared. X squared is equal to the KSP value. So if I take the square root of both sides, I get X. X represents how many moles of lead carbonate are going into solution. How many moles per liter of lead carbonate going into solution. All right, so for every X amount lost, I'm making X amount of lead carbonate, I'm making X amount of lead ion, and that represents the molar solubility. The KSP value for copper hydroxide is 2.2 times 10 to the minus 20 at 25 degrees Celsius. Calculate the solubility in terms of grams per liter. All right, so this is just an extra step. So for every X amount of copper hydroxide I lose, I'm making X amount of copper ion to X amount of hydroxide ion. So this is a important point, right? The concentration of the copper ion is X. The concentration of the hydroxide ion in equilibrium is 2X. So when we plug these into the law of mass action, right, it's 2X squared, right, would represent the hydroxide concentration, which is the same thing as 4X. 4X times X is 4X cubed. So when you have the ionic compound splitting apart to make 1 mole of one cation, 2 moles of the other, it always comes out to 4X cubed. So plug KSP into this expression, right? 2.2 times 10 to the minus 20. Divide both sides by 4 and take both sides to the cube root. And that solves for X. Now, X represents the molar solubility, right? For every X amount that went in, we got X amount of copper ion. So they want it in grams per liter, so we just use the molar mass of copper hydroxide to convert to grams per liter. And we get what they wanted, right? The solubility in terms of copper hydroxide in terms of grams per liter. All right, relative solubilities, right? Looking at these KSP values, you might make the assumption that, hey, silver chloride is the least soluble. And that'd be true in this situation, right? These are all the same, right? They break apart to form X amount of the cation and X amount of the anion. So in this situation, I just look at the magnitude of the KSP value to figure out which is more soluble. So as long as they have the same form of KSP, you can just look at the KSP value to figure out which is more soluble. Not so for this one, right? These are solved differently, right? For every 1 mole of the copper ion that goes into solution, you're getting 1 mole of sulfide. You're getting twice as much silver with silver sulfide, and it's a 2-to-3 ratio when bismuth sulfide breaks up. So you can't just look at the KSP values here. You'd have to solve for the actual solubility to figure out which is the most insoluble. So just looking at this, right, 10 to the minus 73, bismuth sulfide looks like it wins. But when you solve for X for these, right, you get X squared is equal to KSP for copper sulfide. You get 4X cubed is equal to KSP for silver sulfide. And you get 108X to the 5th power for the solubility of, when you're solving for the solubility of bismuth sulfide. So when you solve for X in these, it turns out that the most insoluble one was the copper sulfide. Even though it looks like it has the larger KSP value, less of it's going in because of how you solve for it. All right, predicting precipitation reactions. We did these problems in the last chapter. It's just plugging into the reaction quotient, right? Instead of it being a quotient, right, which has a denominator, these are ion products, right? It's products over reactants. Well, there's no concentration of reactants because they're all solids. So you compare the ion product Q to the K value. If the Q value is greater than K, well then it's got a you're going to have a precipitate form. All right, you've got more ions in the solution than the solution can hold. If Q is equal to K, well then you have a saturated solution and you're just on the cusp of precipitating. And if Q is less than K, then no, you're not at the precipitation point yet. You haven't added enough solid to have it start dropping out. So when 2 milliliters of 0.2 molar sodium hydroxide are added to 1 liter of 0.1 molar calcium chloride, will a precipitate form? So the first thing is getting the concentrations of the things that are precipitating. So if I put sodium hydroxide in with calcium chloride, it's the calcium hydroxide that's going to drop out. So get the concentration of the calcium ion in terms of moles per total liters here. And so calculate moles, right? Multiply the volumes of each solution being added by their concentration to get moles. Divide by the total volume of the solution to get the new molarities now that you've added the two things together. And plug these concentrations into the law of mass action, right? Into the ion product to see whether precipitation is going to form or not, what the magnitude of Q is. So I plug these concentrations in, solve for Q, and compare Q to K. So in this situation, Q is less than K, so no. With these concentrations, you don't have a high enough concentration of the ions to precipitate. So we're not going to get anything dropping out here.